some snags here, and it's popcorn, which is quite noisy, so we'll sort out the solution at the end of the talk. So please don't leave without getting your snacks. Thank you.
Wonderful. Ooh. Okay, welcome everybody. Thank you for taking out what is presumably your lunch break to be here. Okay, just to get a general sense, how many people here already feel like they know roughly how a transformer architecture works? Good. How many people here roughly know how a convolutional neural network works? Okay. How many people here know how a vanilla basic neural network works? Okay. Oh, wow. Okay. How many people here already know about linear regression? Okay. Not everybody. That's fine. So I was actually going to start right from the basics, like really the basics, and try and build up from there to an understanding of roughly what's happening inside of large language models like ChatGPT. And there's a lot of details I'm going to miss out, but I want to give a little bit of intuition as to what's going on. And this is kind of going to be a little bit of a machine learning overview, although there are only certain aspects of machine learning that I'll be able to talk about. We have until 1:45? Yeah, more or less? Okay. Very good. So let's say you are a second-year student. How many of you are second-year students? Okay. And we want to make a prediction about how well you will do in MAM 2. Okay. What might be a fair input for me to make that prediction? What might be a fair number, something that you can give me that might allow me to make a prediction about how well you'll do in MAM 2? Yeah, absolutely. So that would be, a reasonable indicator. How well you did in MAM 1 probably has some relation to how you do in MAM 2. But if you tell me that you got 70% in MAM 1, I can't take that and say, well, you'll probably get 70% in MAM 2. It's clear they're probably related, but we don't know how they're related. And so the question we have to ask is, well, how are they related? How is your first-year mark related to your second-year mark? And what we want to know actually is not how yours is related, because if we find out the value, well, then there's no question to ask. That's just the number. But what we can do is we can look at historical values. So we can say, well, if we take former students, where this is, I'm just going to say first year mark, and this is second year mark, each individual from the past has some mark that they got in first year and some mark that they got in second year. So let's say one particular pupil got 70% in first year and then they got 60% in second year. They're going to sit as a point there. Okay? So now let's say you got 70% in first year. Is it fair now to say that you're going to get 60% in second year? Well, actually, with this information, if that's all the information we have, then that's a reasonable guess. If you're going to guess anything, it's reasonable that you would say, well, given this very, very small amount of information, let's guess 60%. But actually, of course, we're going to have a lot more information from that, from all the hundreds of other students in the past. I guess if you're getting less than 50%, so let's say this is 50%, if you get less than 50%, you're not in second year maths. But let's say that it looks something like this. Okay. There are a few things going on here. The first thing going on is that we see that there's a clear trend. Okay. It seems like if you did better in first year, you are probably going to do better in second year. Okay. But what we also see is that there are clearly some other factors here that isn't simply taken into account. It's not just your first year mark determines your second year mark. Because here we see that one person who got 70 ended up with 50 in second year, and one person here ended up with 60 in second year. So there's clearly some other factors that are important that we're not taking into account here, and that's okay. So we say that there's some noise in the data, and essentially by noise here we mean there are other factors which we're not taking into account. Okay. So how would we make a prediction? So now let's say, somebody comes along and they got 75 for first year. What do we want to do? Well, we could sort of eyeball it and say, well, people who got around 75, well, they seem to range here, so maybe somewhere in the middle there. might be one way to do it. But of course, another way to do it is to draw a line of best fit. Okay? So I can draw a line through here and say there seems to be this trend. Okay? And the data sort of looks like it's a linear trend rather than being quadratic. Maybe we could think of there being a quadratic trend. But for now, everything's going to be linear. We're just going to draw a straight line of best fit through this. Okay? And we can ask here, how good is this line? Okay? How good of a fit is this line? Because clearly if I said, here's the data, and I'm going to make a predictive line which looks like this, you'd say, what are you doing in a maths department? That's clearly not a good fit for this data. Okay? None of the data fits anywhere near this line. This is not a good fit for the data. So the one that I've drawn on there, I think the white one there looks like a reasonable fit. But of course, we're mathematicians and we want to quantify this. How good of a fit is this? So we can think, the first thing that we can think about is the fact that here we've got a straight line, and a straight line here is parameterized by two values. Okay? It's parameterized by the gradient and the intercept. Okay? Those are two values that you can use. Of course, you can describe it in other ways. But this line is y equals ax plus b, where here x is the first year mark and y is the second year mark. I'm actually going to give you a little bit of notation here where, in fact, I'm not going to say y equals ax plus b. I'm going to call this y hat. Okay? Y hat here is my prediction. Okay? The values here I'm actually going to call y. That is to say, a given person has some x and some y. Okay? This is their first year mark, this is their second year mark. And the actual second year mark they get is y. And this line here, which is the line of best fit, is the thing that I'm going to use to make predictions, and I'm going to call this y hat is ax plus b. Okay? And we can see here that, let's say we take a mark here of 60. Okay? We can say, what's the prediction of somebody who got 60 in first year? Well, we go up here and we ask about what's the predicted value here, y hat, based on the line. Okay. We can then ask the question, well, we've got a couple of people here who did actually get 60. This person here and this person here. How far away from the line are they? And actually one of them is above and one of them is below. Okay. So we can say here that for one of the people, there's a gap here. It doesn't perfectly fit through that person's data point, nor does it fit perfectly through that person's data point. So there's some error here. Okay? And of course, what we want to do is to find the line with the lowest error. Okay? What we mean by that is we want to find the sum of I equals 1 to n, where I is the pupil number, or student number. And by student number, I just mean the first student in the data and the second student in the data, et cetera, et cetera. We're going to sum over all of them up to total number of students. And we're going to take the difference between the predicted value and the actual value for each student. Okay? So that's going to be yi minus yi hat. And we're going to square it because we don't mind whether the error is above or below the line. Seems reasonable? Okay. So what we mean here is, what's the actual second year mark for student I? And here we mean, what's the predicted mark for student I? Okay. So remember yi, or y hat here, is just ax plus b. So I can rewrite this as the sum, I equals 1 to n, yi minus axi plus b squared. Okay? So xi here is the actual first year mark. Yi here is the actual second year mark. And a and b are two parameters. And as I change a and b, it's going to change the slope and the intercept of this line. Okay. So what we can say is that this is what's called a loss function. It's essentially the error that says, what are we unable to predict here? How good is this line at predicting the data? So this thing here, which I'm going to call L for now, this loss function, what's it a function of? So xi and yi are given. That's our data set. That's the points here. We can't change that. A and b, on the other hand, are parameters, and we can change those. So I can think that L here is a function of A and B. Okay. So if that's the case, then I can think about plotting L as a function of A and B. Okay. And, well, it's going to be quadratic here. So in fact, it's going to be some surface that looks maybe something like this. Okay. Well, what this means is that if I take some particular value of A and B, some point there, which is going to correspond to some line here, maybe that value of A and B there corresponds to the line that I drew earlier, which is not a very good fit. Okay? It says that the loss or the error is relatively high. What we clearly want to do is to find the value of A and B which minimizes this error, that makes the sum of the squared differences between the prediction and the actual value as small as possible. Okay? We happy with this? Yeah. Please ask any questions if you have them. Okay. So what we want to find is, what is this value? And I'm going to call it A star, B star, which is the value of A and B that minimizes the error, that makes our predictions as close as possible to the actual values. Okay? And that's machine learning. Okay? I've got some data here, and I'm going to have some algorithm that, given some starting line, or some starting value of A and B, allows me to move down this two-dimensional surface in this case, so that I can find the optimal values A and B that predict the data as accurately as possible. Okay. And we can do that using calculus. Okay. Essentially, we can say, I'm at this point here, what are the gradients of the loss function with respect to my parameters A and B? Okay. And from that, I can say, what's the direction in this space of the steepest gradient? Okay. I've got some bowl. Looks something like a bowl here. Okay. I'm at some point on the bowl. How do I move from the point on some point on the side down to the bottom just by using local information? And the answer is, well, let's move around and find what's the direction of the steepest gradient, and move a little bit in that direction, and then ask the question from that new point AB, and then do it again and again and again. And in fact, if you do that, you will end up close to the bottom. Okay? When I say close to, it's going to depend on the step size. Okay? If I'm on the surface of the bowl, and I take the same step size each time, well then maybe I'm going to actually move over the optimal point, and then I'm going to move back, etc., etc. It's going to depend a little bit how I do it, but theoretically I can then find the minimal value here, which is the line of best fit. Okay, we happy with this? Okay, so what's this got to do with neural networks? Well, the answer is everything. Okay. So let's to start with think about how we might encode this in some graphical way. And I'm going to draw a box, and I'm going to draw an input, x, and I'm going to draw an output, y, and I'm going to put a b there, and I'm going to put an a here. Okay. So what this little diagram tells me is that I'm going to pass x into this little machine. I'm going to multiply it by a, and this is what's called a bias term, and I'm just going to add it on. And the outcome here, actually I should call that y hat, the outcome here is indeed x times a plus b, xa plus b, and that's the output. Okay. This is a really, really simple, well, in fact, it's not really a network, but you can sort of think of this as a neuron. And this is motivated actually from the way neurons work in the brain, which is the input signals come into each neuron, and depending, in that case, on the sum of all of the inputs, the neuron fires or it doesn't and passes information on to the next neuron in the network. So what we've looked at so far is one outcome variable, y, being dependent on one input variable. Okay. But in fact, probably some other information is important here. maybe we want to include not just the first year marks, but maybe the average number of hours worked per week, studied per week. That seems like that's probably also going to give you some relationship with your second year marks. Okay? If you study more, you will probably do better, I hope. Okay. And so we can think then that rather than having this plot on a two-dimensional plane, we have a plot where here it's first year marks. I'm going to call this hours worked and second year marks. And again, we can do the same thing. Okay? But in this case, the points are going to live in this three-dimensional space now. Okay? And we can think not of having a line, but some surface. Okay? So there's a surface now in this space where the value of the second year marks is a function now of the first year marks and the amount of study that the person does. Okay? In fact, how would we write this? Well, we could write, I'm going to write y hat. The output is still just a single variable. Y hat is, now let's call this x1. That's the first feature. We're going to use the first year marks. And let's call the hours worked x2. Okay? So now this is going to be, actually I'm not going to call it A and B anymore. I'm now going to call it W1 x1 plus W2 x2 plus B. B will alter the height. W1 and W2 will alter the gradients in the two directions. Okay? So I happened to call it A and B before, now I'm calling it W1 and W2. I called it X before, now I'm calling it X1, which is the first year mark, X2, which is the number of hours worked. So this seems like a reasonable, we call it a model. This is a model of how well someone is likely to do based on their first year mark and the amount of hours worked. And now we have three parameters, W1, W2, and B. How could I write this in this form? Well, I can write it like this. I've got x1 coming in and x2 coming in, multiplied by w1 and w2, and add b. And the output of this is that I do x2 times w2, x1 times w1, add them together, add on the b, and that's the output. So y hat is x1 w1 plus x2 w2 plus b. So now I have three parameters. Previously I had two, I had a and b. Now I have three parameters here. Okay? B and W2 and W1. But that's fine. The methods that we use to move down this surface are exactly the same. Okay? Just a bit of calculus. Okay? You take derivatives with respect to W1 and W2 and B, and you move in the direction of steepest gradient. It's called gradient descent. Okay? This thing here is what's called a perceptron. It was developed in 1958 by Frank Rosenblatt, and he wasn't dealing with a problem like this. He was actually dealing with a problem with images, and in this case, image recognition. So far I've dealt with a problem which is a regression problem, and a regression problem essentially means I give you some generally continuous input, and I want to give a continuous output. So there's a continuum of values that you could get in first year and a continuum of values you could get in second year. But there's another type of problem that I could think about, which is a classification problem. So let's now say that there are actually two input variables. So let's think about an example of COVID outcome. Okay? So maybe over here we have age, and maybe over here we have blood pressure. Okay? So in general, people who were older or had higher blood pressure, maybe their outcome was not so good if they got COVID. And so we could start to put individual people on here, but this is no longer a continuum. Now they did well or they didn't do well. And we're going to say that if they did well, we're just going to put a 0 there. So each one of these is a person who got COVID and then was okay afterwards. And X's are going to correspond to people who got COVID and didn't do so well. Okay? So now, this is a classification problem. Now I can say, given some new person who comes along to the hospital, there's some particular age and they've got some particular blood pressure. Let's say their age is over here and their blood pressure is over here. Okay? And we want to make a prediction as to how they're going to do. Well, they're going to sit at this point here, and we can see, looking at this data, well, you know, they're sitting within the ones who didn't do very well, so they're probably not going to do very well either. But there's a mathematical way we could do this, which is to put in a decision boundary. Again, I can put in a straight line here. Okay? And I can say my prediction is that anybody who is below the straight line is going to do well, and anybody who is above the straight line, I'm predicting that they're going to do badly. And again, I can come up with an error in the predictions. So for instance, let's say this was my decision boundary. I see that these would be incorrectly predicted. Okay? So of course I want to find the line that best slices through this space and separates one class from another. Okay. Good. And we can think about doing this in higher dimensions as well. Let's say actually age, blood pressure, and some other variable, I don't know, resting heart rate was another variable which tells you something about the COVID outcome. Then we'd have a three-dimensional space, and we wouldn't have a straight line, we'd have a plane. Okay? At the moment, all of these are straight lines. Everything is linear here. Okay? Of course, in reality, it isn't, and there will be ways that we can include nonlinearities. But we can think now that we have some space, three-dimensional space. We have a load of people up here. We have a load of people down here. And there's some decision boundary, which is, in this case, some flat plane. Okay? Of course, it's an infinite plane, okay? But it separates the space into two parts. Okay? And what we're saying here is that over here live the people who didn't do very well with COVID, and down here live the people who did do well with COVID. Okay? So let's go to a much higher dimensional example. Okay? I'm originally a string theorist, so I like high dimensions, but we're going to go even higher than most string theorists like, and let's go up to 1,000,000 dimensions. Okay. What sort of thing has 1,000,000 dimensions? Okay, so here we have data where, well, there's just two dimensions, there's age and there's blood pressure. What sort of input data might have 1,000,000 dimensions? An image, exactly. So let's say we have a megapixel image. Okay? We have an image here, and maybe it's a handwritten image of a 3. Okay? So here's some handwritten image of a 3. Okay? But of course, if this is a digital image, it's pixelated. Okay? So it's pixelated, so I can split this up like this, where each individual pixel, of course, the pixels are going to be much smaller than this, but let's say the pixel values are either 0 or 1. It's a black and white image. Okay? 0 here says that there's nothing there, so this particular pixel value is 0, and let's say this particular pixel value is 1. Okay? So I can take my 1,000,000 dimensional image here, or 1,000,000 dimensional, no, this is 1,000 by 1,000, let's say. Okay, so we've got 1,000 down here and 1,000 here. So overall we have 1,000,000 pixels. And what we might want to do actually is to flatten it out. So we'll take this row of pixels, and then we'll just concatenate, we'll put onto the end of it this row of pixels. So rather than it being 1,000 by 1,000, it's a 1 by 1,000,000. Okay? So all I've done there is I've taken my 1,000 by 1,000 and just taken each row and just put them next to each other. Same information is encoded there. Okay. So now, if I think about this as a 1 by 1,000,000 dimensional vector, here, this information here is a 3-dimensional vector. So this individual point there might be somebody who is age 73, blood pressure 150, let's take the diastolic blood pressure 150, and let's say their resting heart rate is 75, okay? So that is the position in this 3-dimensional space, okay? It's just that position, that's the coordinates. Here, what do we have? Well, we have 0, 0, 0, 0, dot, dot, dot. And then when we get onto this part, we'll have maybe 0, 0, 1, 1, 1, 1, 1, 0, 0, etc., etc. Okay? So all we're saying here is that we're just reading off, we're going along each individual pixel value, okay, and writing it down. We've now got 1 million of these numbers. Okay? This is a million-dimensional vector where it's either zeros or ones. But now let's think about where it lives in a space. Okay. So let's now imagine that this is a 1 million dimensional space. Of course, I've drawn it as 3-dimensional, but imagine that there's 1 million dimensions there. Okay? This is a single point in a 1 million dimensional space in the same way that this is a single point in a 3-dimensional space. Okay? So this sits over here. This image is that point in a 1 million dimensional space, okay, where each of the directions is the 0 or 1-ness of each of the pixels. Either there's something there, like here, or there's not, like there. Okay? This is one particular 3. I could draw the 3 slightly differently. There's another 3. And there's another 3, and there's another 3, and there's another 3, and there's another 3. Okay? One can imagine that in this million-dimensional space, all 3s are going to sort of live in the same area. Okay? And there's going to be some density of them. You know, over here, there are things that are sort of like 3s, but these are kind of really characteristic 3s. Okay? There's a distribution. Okay? In fact, 3-ness fills a distribution within this million-dimensional space. Okay, there's a lot to think about there. But you can think that I could sample from here. I can take a point here where I haven't drawn any 3, and I could say, what does this image look like? And I can reproduce it, and maybe it's a 3 that looks like that. Okay? In fact, I can generate. That word, generative AI, is essentially associated with this. It's about understanding this distribution and sampling from this distribution to create new instances. What's this got to do with neural networks? Well, in this case, this was 2 inputs, 1 output. Okay. Here I've got 1 million inputs. So what I could think about doing would be to have each of the pixel values, all 1 million of them, multiply what W1, W2, dot, 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 W10 to the 6, okay? They all go in here, there's some bias term added, there's an output, and of course what I want to know here is it a 3 or is it not a 3? Okay? So I might put on some thresholding function that says, maybe this says if output greater than 0, then output 1, else 0. Okay? I mean, it's just a function that looks like this. Okay? So I take the pixel values, I multiply them by these parameters, and add b, and then I pass it through this function that if the output is less than 0, I output 0. If it's above 0, I output 1. And 1 corresponds to there being a 3 there, and 0 corresponds to the image not being a 3. Okay. However, there's a bit of a problem here. And the problem, of course, is what I've drawn here, corresponding to kind of a larger version of this, can only ever give me a straight plane. Okay? And there's no reason to think that the distribution of 3s in this million-dimensional space, we have to be a little bit careful here. We can always separate some distribution from the rest of the space with a straight plane. But now imagine I've got 3s over here and 2s over here. Okay? So 3s are sitting at this point here, and maybe 2s sit here. And what I really want is some separation like this. Okay? I can't do that with a flat plane. So I need to add a little bit of nonlinearity, and I want to be able to write a general function. So in fact, the way we do this is in this case, we're going to write what's called a fully connected feed-forward neural network. Okay? So it's just a generalization of this. So rather than having one of these perceptron units, let's make a load of them. Say we have 4 here. And what I'm going to do is I'm going to pass the million pixel values. Okay, there's a million pixel values, and they're all going to go into this one. Okay, in exactly the same way here. Okay, multiplied by some set of weights. Okay, and there's going to be some output here. But those values are also going to be passed into this perceptron. With some different set of weights. Okay? Remember, the point about the weights was that the W1 and W2 are things that I can move around to get the lowest loss function, to get the lowest error. Okay? I move along my surface using gradient descent until I find the value of the parameter which gives me the best match to the data that I have. Okay? So in this case, I'm going to have 1,000,001 parameters, W1 up to W 10 to the 6, and there's a B there as well. Okay? So there I've got 1,000,001 parameters, and I'm going to move around in my 1,000,001 dimensional vector space, parameter space, until I find the minimum of the loss function, which says the difference between the input data and the prediction, squared, et cetera, et cetera. Okay? All I'm doing here is I'm just doing the same thing, but now I've got a number of these, so I'm going to have more weights here. Why is this of any use at all? Okay, I'm going to take the outputs of these, so now there's maybe only 4 outputs, and I'm going to do the same thing. Maybe I'm going to put another layer in, another layer of perceptrons. So here, each of the outputs is going to go into this with another set of weights, and into this with another set of weights, okay? And finally, maybe they're going to come together like this, and there's going to be some output, some prediction. What this allows me to do is to approximate more complex functions, because that's what we're doing. So from first year, you will remember that the data that I put up there, originally, the first year to second year data, that's a function. It's defined by the data itself. Okay, I've got an input, and and there's an output. We've got to be a bit careful in case there's 2 outputs for the same input, but let's forget about that for now. And what we're trying to do here is we're trying to find an approximate function. Okay, in this case, we're approximating it by a straight line, but maybe a straight line isn't the best thing to approximate it by. Here, it looks kind of complicated, but essentially all we're doing is we're taking the pixel values, which in this case are 0s and 1s, it's a black and white image. We're multiplying by a load of weights, adding on some bias for each of these, okay? Taking the outputs of that and passing it into another layer, and then another layer and an output. This whole thing is just a function. I can put in any value here, and it's going to output a value there, okay? And I can compare the output value with the true value, 1 or 0. Was it a 3 or wasn't it a 3? Yeah.
For your approximate function to be nonlinear, though, don't you need to aggregate?
Good. So at the moment, this is still linear. Okay? Essentially, everything that I'm doing here, in fact, the way we write all of this, okay, is just matrix multiplication. That's all it is. It's just matrix multiplication, and the gradient descent is just a little bit of calculus. Okay, so how might we make this nonlinear? So I spoke here about the fact that here I've got this nonlinear separatrix, separating surface between this data and that data. Okay, the way we do it actually is that we take the output here and we just pass it through some very simple nonlinear function. Okay, the simplest nonlinear function we can use is actually something called a rectified linear unit, where here's the output of this neuron, okay, and the output after the activation, it's called an activation function, is linear, which seems to be linear, apart from the fact that it's linear piecewise defined. Okay? the output, the activation after going through the function, is exactly the same if the value is greater than 0, and is 0 if the value is less than 0. And actually, this strange piecewise defined function that I'm just going to plonk in after each one of these perceptron nodes, okay, that's enough to actually give you a nonlinear separating surface. Not only can I give some nonlinear separating surfaces, I can give every single one, up to some discussion about sort of continuity and differentiability and various things, but actually any function within a very large class of functions can be approximated by this neural network. There's actually something called the universal function approximation theorem that says if the neural network is large enough, I can approximate any function. Okay, smoothness, etc., notwithstanding. Yeah. Sure. So let's think about this for the really, really trivial case where we've got, let's say, 2 inputs. Okay? So all this is going to say is I've got my input x1, input x2, I've got my w1, w2, b. There's an output of this, which is x1, w1 plus x2, w2 plus b. And then this passes through a nonlinear function where this function might be the ReLU activation function. Okay? So if this value is greater than 0, just output the same thing. If it's less than 0, just output 0. Okay? It's a really trivial nonlinear function, and in fact it's piecewise linear. Okay? But it's enough to be able to generate a very, very large class of functions. Okay? And that's what we're trying to do here. We're trying to create a thing that can approximate functions. Okay? Here we're trying to approximate the relationship between first year and second year marks. Yeah. So I think we have to be a little bit careful with sort of approaching the data, because remember the data here is the x1, x2 values within the space. By the time you get here, you've multiplied by the values here, and particularly when you have multiple hidden layers, so multiple layers within your neural network, you're essentially dealing with a different representation of the space. So within that space, that might be the case. Yeah. So we have 8 minutes for me now to explain transformers to you. That may be a little difficult. Okay, but I think we can get some way there. So here we've seen that we can take images, and generally to train this neural network, I take loads of images, I transform them all to these vectors, I pass them through the neural network, I start off with random weights, w1, w2, w3, etc., etc. They're all completely random to start with, in the same way that with this diagram, we started at some value of a and b, and then we moved down the surface bit by bit until we found the line of best fit. In exactly the same way, we pass all of the pictures into this. We're going to get some sum of squared errors, okay? And we're going to change the values of w1 and w2. There's going to be maybe a billion values here, probably not a billion in this case. There's going to be several million values here, and we're going to move down this million-dimensional surface until we find the value which has the lowest error in predictions. And we can then use that to predict on unseen data. Sorry, my shoelaces are coming undone. Okay. So we can deal here with images. Great. What else might we want to deal with? Well, we can think about dealing with sequences. Okay. So an example might be sentiment analysis. So let's say I've got a sentence which was, the movie was great. And I want to pass this into a neural network, which sounds weird to begin with, and I want the output to be whether it's a good movie review or a bad movie review. And the movie was great, sounds like it's probably a positive movie review. So how on earth would we do that? Well, this is all linear algebra, essentially, multiplying a vector by a load of matrices, and then doing a bit of calculus to find the lowest point, okay? But how would I pass in the movie was great? Okay. So I need to turn each of those words, in fact, not just into a number, but into a vector. Okay. Let's think about this. So in the same way that each individual image corresponds to a single point in some high-dimensional space here. So here I've got megapixel image. It's a single point in a million-dimensional space. I can think about embedding a word into a high-dimensional space. So here I've got some really high-dimensional space, maybe 100,000 dimensions. And over here is a vector, and the point here corresponds to the word movie. Why this particular point? Well, in fact, the embedding, the way you put the words into the space, that's something which is learned, and I'm not going to go into the details of that. Over here, we've got the word the. Over here, we've got the word great. Historically, sequence data like this, where the order is important, the movie was great, that order is really important, was dealt with using what's called a recurrent neural network. When I tell you that sentence, I say the, and then I say the word movie. When you hear the word movie, you have in your memory the fact that I've already said the word the, okay? And you're updating your memory. The, then comes movie, and now I've got this sort of composite thing in your brain, which is the movie, okay? And then I say the word was, and you take the movie concept, and now you see the word was, so there's some sort of past tenseness to it, okay? And then the movie was, there's something about the past tense of a movie, and then there's the word great, and it comes in. So you need some memory to deal with this, okay? So a recurrent neural network has a loop which takes the hidden state, the state of your brain as you're hearing the next word, okay, and concatenates it in a particular way with the next stuff that comes in. Well, that's great, unless you have a really, really long sentence, okay? Because if I have a sort of a relatively small unit, which is the thing which is storing the memory, then if I pass in a whole book, well, you don't want to have remembered every single word. It's going to become a mess. So what you want really is to be able to forget. As a word comes in, you want to say, that's not very important. I don't care about the, okay, movie, great. Those are the important words here for the particular task that I'm trying to do. Sentiment analysis. Was the movie good or not? So the next evolution in recurrent neural networks was the so-called LSTM, or long short-term memory. A particular type of network which had a forgetting and remembering component to it, and essentially it was very similar to this. It was just a neural network, but essentially there's a feedback mechanism. Stuff comes in, but there's a loop. And here, this is essentially the memory, okay? And you pass in word by word. Great. The RNN, recurrent neural network, wasn't great because you had to remember everything, and it's not very efficient, doesn't work very well. But if you can remember and forget, then you've got the long short-term memory. I haven't drawn in those modules about the gating, but that's how they work. But they're also not that great for really long pieces of text. So I think I'm coming to the conclusion that I might need to do a part 2 if I actually want to talk about transformers, unless I'm going to talk about it in the next 2 minutes. In 2017, a paper came out called Attention is All You Need, and changed the game. We'd gone from recurrent neural networks up to long short-term memory. These are just different architectures of neural networks. Here, I've got an incredibly simple perceptron. I can put them together to create a fully connected feed-forward neural network. I can include memory parts to make it a recurrent neural network. Actually, when we deal with images, we use the spatial information to use what are called convolutional neural networks. There's another architecture, the LSTM, the long short-term memory, and then 2017, this new paper came along which changed the game. And I think that I will wait until I am invited back again, if I'm invited back again, to give another part where I actually talk about ChatGPT and transformers, if that's right. Awesome. I'm going to stop there for now. Any questions? For anybody who hadn't come across neural networks before, that was probably a lot to take in. But I hope it's given you some sense about how they work. Yeah?
We have one piece of data. Surely we can't estimate that based on that data that we're going to get the same response. Like if I flip a coin once, I can't flip it again and say to myself, it's probably heads because the previous one was heads.
Great. So there is actually a way to deal with very small amounts of data using a sort of more probabilistic method, and it's something called a Gaussian process. And essentially, the Gaussian process works by saying, I'm going to start off with some prior. I'm going to start off with a prior belief about the dice, about the relationship between this variable and this variable. Okay? And it's not just a single straight line, but it's going to be something that says, I think this is probably the straight line, but maybe this one is, and maybe that one is, and maybe that one is there. And then I take a single piece of information, I take a single reading, and I find that it's there. Okay? And then I update my information to say, well, maybe this is the most likely curve, but there's some possibility that it could be these curves. Okay? So there is a way to deal with very small amounts of data using Gaussian processes, which is a sort of beautiful framework for dealing with this. And you end up not just with a point estimate. So in this case, I can say, okay, what do I think is the likely outcome if somebody got 65%? Well, I think it's, I think maybe they got 70 for MAM2. You can actually come out with a distribution, and you can say the likelihood of them getting this value for MAM2 is this. So you can get more information from a Gaussian process than you can from the types of models. So these are sort of probabilistic machine learning models. Yeah. Any other questions? Yeah. Sure. So the question there is, are the current neural networks models still used? Yeah, absolutely. So one has to be very careful when you have a particular architecture that you apply it in the right places. So as an example, if I had this data here about age and blood pressures and an outcome, it would be a terrible idea to apply a transformer architecture to this. In fact, for this data, I wouldn't even use a neural network. Okay? I use a simpler model. So you have to match the model to the type of data and the type of problem you have, and the amount of data very often. So there are lots of models out there. There's a fully connected feed-forward neural network, and absolutely those are still used. But there are certain types of problems that the transformer architecture, which ChatGPT is built on, is particularly useful for. Yeah, so absolutely all of these architectures are still used. Yeah. Any other questions? Okay. Oh, yes. Oh, two questions popped up. Yes.
With the number example,
Yeah.
surely the order of those things matters
Absolutely.
in relation to other things. So if we would leave it as just a matrix of like that image, it would be more efficient, right?
Yeah, so indeed. So when you leave it as an image, basically that's when you use what's called a convolutional neural network. And there, rather than doing it like this, there's actually sort of a little filter that passes over the whole image. And it's exactly like the filter that we have in our visual cortices. No, actually in not quite the visual cortex, but within the visual system, which picks up, for instance, straight lines. So it'll go over and say, where are the straight lines in this image? So it'll say, okay, we've picked up a straight line here, and that then becomes a feature for the next layer. Is there a curve that looks like this? It picks up that feature and passes it through. So yeah, so actually to deal with images, generally you want to include all of that relational data between the different pixels, and there you'll use a convolutional neural network. Yeah.
My question was, how well do AI models such as the transformer model cope with inputs that are chaotic, i.e., random, but being chaotic seems random. Are they able to deal with that at all, or not?
I mean, there's a difference between truly random things and pseudo-random things. So if there is some structure to the data, if the model is powerful enough, then it may be able to pick up that structure. If it's a completely random thing, so for instance, if, for instance, you defined your sets as a set of completely randomly generated images, 100% randomly generated, and you just generated, say, 100 images, and you said, this is my data set, and there's no relationship between them, then no, there's nothing to learn there. It's not going to be able to classify those images because they're just sitting at completely random points within the space. So if it's truly random, then there is no structure for the machine learning algorithm to learn. If it's pseudo-random and there is some hidden structure there, then with a powerful enough network and enough data, you should be able to learn it. Yep. Very good. Okay. In which case, I guess I'll chat with you about whether or not you want an extension to this. Very good. Thank you very much.
Hi guys. Sorry, just before we go, if you'd like a packet of popcorn, it's a bit difficult with the distribution because the numbers are more than me.